Noble gas notation is especially useful when writing the electron configurations for larger atoms with more sublevels. For example, the electron configuration for iodine is very lengthy. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. Iodine's configuration can be shortened significantly by using noble gas notation. Begin by identifying the noble gas in the period preceding iodine, which in this case is krypton. Krypton's electron configuration is the same as iodine's inner level configuration. The highlighted part of iodine's configuration that matches krypton can be written as Kr. Iodine's noble gas notation is krypton 5s2, 4d10, 5p5. All elements in period 5 will have an inner configuration that is the same as krypton's configuration, so the noble gas notation for all elements in period 5 will begin with krypton. In the same way, the elements in period 2 written in noble gas notation will begin with helium, the elements in period 3 will begin with neon, and so on.
And let's take a look at the last one, which is valence electrons and electron dot structure. All right, let's see. Here it is. Last one.
The alkali metals belong in group 1 on the far left side of the periodic table. These metals have similar chemical properties. For example, pure alkali metals are so reactive that they must be stored in oil or in glass vials with the air removed in order to prevent them from reacting with oxygen or moisture in the air. What causes alkali metals to have similar chemical properties? Valence electrons are the electrons that are located in the highest energy level of the atom. Silicon has 4 valence electrons in its highest energy level, the 3rd energy level. It's important to know the number of valence electrons in an element because valence electrons determine an element's chemical properties. In the main group elements, valence electrons are the only electrons used in forming chemical bonds. For main group elements, the number of valence electrons can readily be determined from the element's placement on the periodic table. The valence electrons are the same as their A group numbers. When using the IUPAC group numbers, you subtract 10 from groups 13 through 18 to determine the number of valence electrons for elements in those groups. Using the periodic table, you know that potassium has 1 valence electron, boron has 3 valence electrons, and sulfur has 6 valence electrons. An electron dot structure is a diagram that represents the valence electrons of an element. The element symbol represents the atomic nucleus and the atom's inner electrons. Each dot represents 1 valence electron. Potassium's electron dot structure has its symbol, K, with 1 dot to represent its 1 valence electron. Boron's electron dot structure has 3 dots, representing its 3 valence electrons. Sulfur's electron dot structure has 6 dots, representing its 6 valence electrons. To write an element's electron dot structure, you place the dots one at a time on each of the 4 sides of the element symbol. You may place the dots clockwise or top to bottom to side, but you will always place a single dot on each of the 4 sides before you place a second dot on any side. An element following the octet rule will not have more than 8 dots in its electron dot structure. The octet rule states that atoms tend to gain, lose, or share electrons in order to obtain a noble gas configuration of 8 valence electrons. Hydrogen and helium are an exception to the octet rule, as they are stable with only 2 electrons. The electrons in an atom can be represented in different ways. Electron configurations show the number of electrons in each energy level of an atom. These can also be translated to noble gas notation. Electron dot structures show the number of valence electrons in an atom. All representations are useful for predicting how elements will bond to form compounds.
Alrighty, that's the last one there. Please make sure you answer all the questions that go along with your notes. And don't forget you have the other set of notes as well.